Electric vehicles are everywhere now, but beyond just plugging in, what's really going on under the hood?
Why,
Today, we're kind of cracking open the secrets of EV powertrains.
yeah, looking at the nuts and bolts.
We've got some fascinating breakdowns of the core tech, and our mission is simple, to give you a really crystal clear picture of how these things actually move.
Exactly. It's about moving past just the basic idea of an electric car
Mm-hmm.
and really understanding the elegant engineering that makes it all work.
Okay, let's dive right into, I guess, the heart of it all, the battery pack. It's essentially the fuel tank,
So
right?
that's a perfect way to put it, yeah. The battery pack is the energy reservoir for the whole vehicle.
Okay.
And the magic inside happens thanks to lithium-ion chemistry. You might hear about different sort of flavors of these batteries,
Flavors, like what?
like NMC, that's nickel, manganese, cobalt, and LFP, which is lithium iron phosphate.
So NMC, LFP, are these different types better for different things? It's not just like one size fits all.
Precisely. Yeah, you've hit it. NMC batteries often offer higher energy density,
Meaning.
meaning they can store more energy for a given size and weight.
Hmm.
So that can translate to longer range.
Right, okay. More miles per charge.
Exactly. LFP batteries, on the other hand, they tend to be more cost-effective. They have excellent thermal stability and often a longer lifespan.
But the downside.
They might be a bit heavier for the same amount of energy. So you see, it's a trade-off. Depends on the vehicle's, purpose and price point.
Interesting. So it's definitely not just a big box of AA batteries stuck together, I imagine.
Ah, no, not quite. These lithium-ion cells, they're grouped together into larger assemblies. We call them modules.
Modules.
And kind of orchestrating this whole power ballet is the battery management system, or BMS.
The BMS, that sounds like the unsung hero here. What's its job description? What's it actually doing?
Think of the BMS as the guardian of the battery pack. It really is. It's constantly monitoring everything, the temperature of each cell, their individual voltage, the amount of current flowing in and out,
Wow.
and critically, the overall state of charge, how full the battery is.
And why is that monitoring so important?
Well, it's absolutely crucial for safety, for one, preventing overcharging or overheating, which, can damage the battery and definitely shorten its life.
Right. Makes sense. So it's not just passively holding energy, it's actively looking after it. And what does this energy actually power?
It's the central power source for, well, pretty much the entire vehicle.
Everything.
Primarily, it sends high voltage DC power to the inverter, and we'll definitely talk about that
Well,
next.
good.
It also feeds the car's regular electrical systems, your lights, your infotainment, all that stuff, through something called a DC-DC converter.
Right. Stepping down the voltage.
Exactly.
Yeah.
And really importantly, it's where the energy captured during regenerative braking goes to get stored back.
Ah, okay. So it's a two-way street for energy there.
Absolutely. It's the heart of the vehicle's energy system, truly.
Okay, the battery is the heart.
Yeah.
Got it. Now, the inverter, you called it a power translator before. What exactly is it translating?
Exactly, a translator. So the battery pack speaks in direct current, or DC.
Right.
But the electric motor, the thing that actually turns the wheels, it typically runs on alternating current, or AC.
Okay, different languages of electricity.
You got it. So the inverter's main gig is to seamlessly convert that DC power from the battery into the AC power the motor needs to, well, do its job.
So it's literally flipping the script on the current. And I remember you saying it does something during braking, too, regenerative braking.
You got it. When you hit the brakes in an EV, or even just lift off the accelerator often, the motor can act like a generator.
Okay.
And it produces AC power when it does that. The inverter then reverses its role. It converts that AC power back into DC power and sends it back to the battery. That gives you that feeling of deceleration, and crucially, it puts energy back into the system.
That's brilliant. So you're reclaiming energy.
It's a really smart way to recapture energy that would otherwise just be lost as heat in traditional brakes. I mean, in some driving conditions, you can recover a significant percentage of your energy this way. Really boosts efficiency.
That makes a huge difference. What kind of tech allows this power conversion to happen so efficiently? It sounds complex.
Yeah, it is pretty sophisticated.
Yeah.
Modern inverters rely on some advanced semiconductor devices. You might hear terms like IGBTs,
IGBTs.
insulated gate bipolar transistors, and increasingly SiCl MOSFETs.
Okay, alphabet soup there.
Yeah. Silicon carbide, metal oxide, semiconductor, field effect transistors. Just think of these as super fast, highly efficient electrical switches.
Switches.
Yeah, switches that can handle the really high power demands of an EV while minimizing energy loss as heat. They're absolutely key to making the whole system work smoothly and, well, efficiently.
So it's not just a simple on-off switch then. It's precisely managing the flow and direction of, like, massive amounts of power.
Exactly.
What else is the inverter responsible for? Is it just the conversion?
Oh, no, beyond the AC-DC dance, the inverter is also basically the conductor of the motor's performance.
The conductor.
Yeah, it controls the amount of torque the motor produces. That's the rotational force that gets you moving, right?
The grunt.
Exactly.
Oh.
It also manages the precise timing of the power pulses sent to the motor, and ultimately, it dictates how fast the vehicle goes. It's
Yeah.
a very sophisticated control center.
Okay, so, wow. Battery inverter. Super important. All right, we've got the energy source and the power translator. Now for the muscle, the bit that actually moves the car, the electric motor.
The electric motor is truly the workhorse of the EV powertrain, no question. Its sole purpose is to take that electrical energy it receives from the inverter
Yep.
and convert it into mechanical torque, that rotational force we just mentioned, which then spins the wheels and propels the vehicle forward. It's where the rubber meets the road, so to speak.
And are all these electric workhorses, created equal? Are all EV motors the same type?
Not at all. No, there are three main types you'll typically find in EVs today.
Okay.
First, there are AC induction motors. These are, well, older designs, known for being simple and pretty rugged.
Okay, reliable maybe?
Yeah. Then you have prominent magnet synchronous motors,
Mm-hmm.
or PMFM.
PMSM. Heard of those?
Right. These are increasingly popular. Why? High power density and great efficiency. They can pack a lot of punch into a relatively small package.
More power, less space.
Exactly. And finally, there are switched reluctance motors, or SRMs.
SRMs.
Yeah. These are interesting because they don't use permanent magnets.
No magnets. Why is that good?
Well, it makes them potentially more sustainable. Concerns about rare earth magnets and durable, though the trade-off is they can sometimes produce a bit more noise or vibration.
Interesting. So different designs with different strengths and weaknesses. And you mentioned earlier that these motors are bidirectional.
Yeah.
How does that work?
Yes, that's a crucial feature because they can operate in reverse,
Yeah.
effectively acting as generators.
Right.
EV motors are inherently bidirectional. This is the fundamental principle behind that regenerative braking we talked about.
Right.
The motor captures the kinetic energy of the slowing vehicle.
The movement energy.
Exactly, and converts it back into electrical energy, which, via the inverter, gets fed back to the battery.
That explains why EVs often have such a smooth deceleration, almost like engine braking, but, well, electric.
Precisely.
Mm-hmm.
And what are the key things you notice when driving a car powered by an electric motor? What's the feel?
Well, the most immediate thing you'll notice is the instant torque.
Yes.
Unlike gasoline engines that need to rev up, electric motors deliver their maximum pulling power right from, 0 RPM.
Instantly.
Yeah. This translates to very quick and really smooth acceleration. And, of course, the almost silent operation is a huge difference compared to the, noise and vibration of a traditional engine.
Definitely quieter.
Okay, so the motor is spinning, creating this rotational force. Now, in a regular car, that force goes through a transmission with multiple gears, right, to manage speed and power. But EVs are different here.
That's a key distinction. Yes,
Yeah.
unlike gasoline vehicles with their complex multi-speed transmissions,
Yeah, lots of moving parts.
the vast majority of EVs use a single-speed reduction gear.
Just one gear, how come? Why is that?
It all goes back to that wide torque band we discussed earlier.
Ah, the instant torque thing.
Exactly. Electric motors produce strong torque across such a huge range of speeds, from 0 right up to very high RPMs. So there's really no need to shift gears to stay in the engine's sweet spot of power like you have to with gasoline.
Uh-huh.
The motor can deliver ample power, whether you're starting from a standstill or cruising on the highway, all in one gear setting.
So what exactly does this single-speed reduction gear do then if it's not shifting?
Its main job is basically to take the very high rotational speeds of the electric motor, and we're talking, upwards of 10,000 RPM, sometimes much more.
That's fast.
Oh, yeah. And it reduces those speeds down to speeds that are actually usable for the wheels. Think of it as just a fixed set of gears that optimizes the motor's output for driving the wheels. It's a bit like the final drive gear in a multi-speed transmission, but, well, it's the only one.
That makes perfect sense. Simpler, lighter, probably more reliable with fewer things to go wrong.
Exactly. Benefits all around. Simplicity, efficiency, reduced mechanical complexity.
But you mentioned there are exceptions. Not all EVs are single speed.
Correct. A few high-performance EVs, the most notable example is probably the Porsche Taycan.
Ah, okay.
They've opted for a two-speed transmission. This second gear can provide, well, even quicker acceleration at higher speeds and potentially improve efficiency during high-speed cruising.
For track days, maybe?
Something like that, or just ultimate performance. But these are still relatively rare. They represent a more complex and, frankly, costly approach. For most EVs, the simplicity and efficiency of a single-speed reduction gear are really the winning formula.
Right. Keep it simple. Okay, so we've covered how the EV gets its go power. Battery, inverter, motor, reduction gear. Now, how does it get its energy back in the first place? Let's talk charging and the onboard charger.
Right, so when you plug your EV into an AC charging station, whether that's the charger in your garage, a level 2 charger at work, or a public one.
The common ones you see around.
Exactly. The onboard charger is the component that takes center stage then. Its job is to convert that alternating current, the AC coming from the grid, back into the direct current, the DC, that the battery can actually store.
So it's another AC to DC converter in the system, but this time working in reverse from the inverter's main job when driving.
Precisely. Think of it as the gateway for replenishing the battery's energy reserves from an AC source. And the speeds at which this happens can vary quite a bit.
Okay, what kind of charging rates are we typically looking at with this onboard charger?
Well, typical onboard chargers have capacities ranging from around, say, 3.3 kilowatts, which is quite slow, up to maybe 11 kilowatts or even 22 kilowatts in some higher-end vehicles. The actual charging rate you'll experience depends on both the capacity of the onboard charger in your vehicle and, importantly, the power output of the charging station you're connected to.
Right, you need both to match up for the best speed.
Exactly. A higher kilowatt rating on the onboard charger means potentially faster charging from an AC source, assuming the source can supply it.
And it's not just like blindly feeding power into the battery, I assume. That sounds a bit risky.
Oh, absolutely not. No. The onboard charger is a smart piece of kit. It's tightly integrated with the vehicle's overall power electronics, and it constantly communicates with the battery management system, the BMS again.
The Guardian is involved here too.
Absolutely. This ensures that the battery is charged safely and efficiently. It prevents overcharging, manages heat, and basically maximizes the battery's lifespan. The BMS tells the onboard charger exactly how much power the battery can safely handle at any given moment during the charge cycle.
Smart charging. And I'd imagine all that electrical conversion, AC to DC, must generate some heat. Does the onboard charger handle that too?
Yes, thermal management is a critical aspect of its operation. It plays a role in dissipating any heat generated during that AC to DC conversion process.
Why?
Well, to prevent overheating, which could affect charging efficiency and the longevity of the charger itself, and potentially even the battery if the heat isn't managed properly.
Right. Heat is generally the enemy of electronics and batteries.
Pretty much, yeah. Keeping things cool is important.
This has been incredibly insightful, really getting a feel for the components. Now, let's gaze into the crystal ball a bit. What exciting advancements are on the horizon for these EV powertrains? Where's the tech heading?
Oh, the future of EV powertrains is buzzing with innovation. It really is. One really promising area, maybe the most talked about, is solid-state batteries.
Solid state. Heard a lot about that. What's the big deal?
Well, they have the potential to be a genuine game changer. They promise significantly higher energy density.
More range again.
Exactly. Longer driving ranges without needing bigger, heavier batteries. They could also potentially charge much faster and be inherently safer than current liquid electrolyte lithium-ion batteries.
Safer how?
Primarily, a much reduced risk of thermal runaway. That's when battery fires can happen. The solid electrolyte is less flammable.
Okay, that's a big plus. So potentially smaller, lighter batteries with longer range, quicker charging, and safer. Sounds almost too good to be true.
Well, exactly. And because they're expected to be more stable and robust, they could also allow for more compact and flexible vehicle designs, while there are still, significant technical hurdles to overcome.
Like what?
Things like scaling up manufacturing cost effectively and ensuring really long-term reliability and durability out in the real world. But the potential is enormous. Lots of investment going into it.
Definitely one to watch. What about the idea of just like parking your car and it charges itself? I've heard talk of wireless charging.
Yes, wireless charging or inductive power transfer is definitely gaining traction.
How does that work? Magic.
Feels like it sometimes. The basic idea is you'd park your EV over a charging pad, usually embedded in the ground or on the surface.
Okay.
And energy would be transferred wirelessly through electromagnetic fields from the pad to a receiver coil in your car, recharging the battery without needing any cables or plugs.
Wow. Imagine the convenience. Just park and forget.
Exactly. Never having to remember to plug in, especially overnight at home, while the charging speeds are currently, generally lower than wired fast charging.
Right, it's not super fast yet.
No, not for high power yet.
Yeah.
But it's a very promising technology for convenient top-ups, maybe at home, work, or even potentially dynamic charging while driving someday, though that's further off.
That sounds incredibly convenient for just everyday life. What other advancements are maybe less flashy but still important?
Well, advanced thermal and energy management systems are going to become even more sophisticated.
Managing the heat again.
Yes, but more intelligently. These systems are crucial for maintaining the optimal operating temperatures for all the powertrain components. The battery, the motor, the inverter, the charger,
Why is that so critical?
to maximize performance, extend their lifespan, and crucially, enable faster charging capabilities without damaging things. We'll see more intelligent systems that can precisely control cooling and heating cycles to ensure peak efficiency in all kinds of weather and driving conditions.
Yeah, okay, smarter management behind the scenes. And I've seen the term integrated drive units popping up more. IDUs, what are those all about?
Right, integrated drive units, or IDUs, they represent a trend towards combining several key components, usually the electric motor, the inverter, and the reduction gearbox, into a single compact unit.
Putting it all together.
Exactly. This integrated design offers several key advantages. It reduces the overall weight and the number of parts in the powertrain.
Which is good for efficiency.
Yes, potentially leading to improved energy efficiency and maybe lower manufacturing costs too, fewer bits to assemble. It also creates a more streamlined and efficient transfer of power. They're becoming quite popular, especially for modular EV platforms where you can slot these units in easily.
Makes sense. Packaging it all neatly. This has been an absolutely fascinating journey into the core of EV technology. It's really incredible to see the level of engineering and innovation packed into these vehicles.
It truly is. I mean, from the battery pack, that vital energy store, to the inverter, the crucial power translator, the electric motor, the force behind the wheels, the efficient single-speed reduction gear, and the smart onboard charger, each component plays an absolutely indispensable role.
They all have to work together seamlessly.
Perfectly. And with these exciting future innovations we touched on, like solid-state batteries and wireless charging just on the horizon, the evolution of electric mobility is, well, it feels like it's really just getting started in many ways.
It really makes you think about the broader implications of all this, doesn't it? I mean, not just for how we get around, but for the entire technological landscape.
Absolutely.
What will these changes mean for our cities, our energy infrastructure, and ultimately just our daily lives?